All right, here's a quick solution for number 11 from the recent test. You have it in front of you, hopefully, but remember that we have a table, and on the table is a block attached by a string over a pulley to a hook, which I'm just going to draw as another mass. And we're told that we know there is a given velocity and a given acceleration, which means the hook has a certain velocity and the same acceleration. We're given the initial mass of this guy. We're asked for the mass of that guy. We're given the accelerations, velocities, and we're given the tension as 2.3 newtons. Part A says find the value of the mass of the hook. So we want to, in part A, we want to find M2. As almost always with force problems, the first thing we probably should do is draw our free body diagrams. And we see that we have the tension pulling up on the hook, and we have a weight pulling down on the hook, which would be M2G, and as indicated before, we have an acceleration, in this case downward. So we can say that from the free body diagram, the sum of the forces on the hook is, and we can see here, it's going to be the tension and the weight. So Ft and M2G, but they'll have a different sign because it's accelerating downward. And then from our Newton's second law, we'll see that the sum of the forces is always just M2 times the acceleration, but we have to be careful here because our acceleration is A, but it is also downward. So we have something like this. And then because these things are equal, then we see that these things are equal. So we have Ft minus M2G equals M2 times minus A. And then we solve this over maybe by bringing M2 to the other side. So maybe we add M2G to both sides, and we have Ft equals M2G minus minus M2A, or Ft equals M2 times G minus A, or M2 equals Ft over G minus A, which in our problem was 2.3 newtons over G, which is 9.8 meters per second square, and we were given an acceleration of 0.82 meters per second square. So we get something like 0.26 kilograms. Part B says find the value of the frictional force. So I redraw my free body diagrams. Here we now have that the tension is pulling the block over, and of course there's the weight M1G and the normal force Fn, and then it's on a rough surface, so there's a resistive force Ff. And remember that we still have that it's accelerating with the same rate, but now to the right. So we do basically the same game. We say the free body diagram tells us that the tension and the force are the frictional forces are the horizontal forces. So we have now Ft, the sum of the forces on 1 and the x is Ft and the frictional force, but they have a different sign because they point in different directions. And the second law tells us that the sum of the forces on 1 in the x direction is M1 times A. And now we can just put the A because it points in the same direction as Ft, so it's equally positive. The same kind of game tells us now that Ft minus Ff equals M1A, and maybe we add F1 to both sides, and we subtract M1A from both sides, and we end up with that FF is FT minus M1A, or 2.3 newtons minus 0.35 kilograms times 0.82 meters per second square, which is 2.0 newtons. And then part C says, find the coefficient of friction mu, in this case mu sub k, because the block is axially sliding. We start off by remembering that mu sub k is going to be the frictional force over the normal force. To get the normal force, we use our free body diagram in the vertical directions now, and we say from the free body diagram, the sum of the forces on 1 and the y is Fn minus m1g, but from Newton's second law, the sum of the forces on 1 in the y direction is m1 times a in the y direction, but it isn't accelerating in the y direction, so the whole thing is 0. That tells us that Fn minus m1g is 0, or Fn equals m1g. And again, you probably didn't have to do all of that. You could probably assert that just from the picture, and it would have been fine. So over here we have Ff over m1g, or 2.0 newtons over 0.350 kilograms times 9.81 meters per second square, which is 0.58 as a coefficient of friction.